Hello and thanks for joining us. Today we'll be learning about ZigBee, and in particular we'll be learning about how to test a ZigBee transmitter. Now what I have here in terms of instrumentation is a PXI system. It's basically a computer with some timing and triggering lines. So here's my PXI controller. This is just a PC. And then I have a vector signal analyzer all the way on the right hand side. This particular one goes to 2.7 gigahertz with 20 megahertz of instantaneous bandwidth. And then next to that I have a little preamp module, and this preamp is just cabled over to the vector signal analyzer. Now, to capture this signal, I'll be using an antenna, so I'll pull this off and show you. This particular antenna is actually pretty long. It's better for lower frequencies, and isn't really optimized for 2.4 gigahertz, which is what ZigBee's at. But in this case, it should work and at least give me some measurements. So we're going to use this antenna to pick up our ZigBee signals. So I'll put that on there. And then, of course, obviously I need a transmitter. And I have one of those actually right here, kind of in front of you. I'll let you zoom in on this a little bit. But this is an evaluation module from Freescale. And on it, it has a little antenna, which is going to be the interface for those ZigBee signals. Now, to set this up, what I'm going to need to do is first I'll plug in the power cable, and then I need to get this particular device in transmit mode. Now, I'm going to hold down the S101 and the S106 buttons right here. Then I'll remove my finger from the S106, and then remove it from the S101, and it should be in transmit mode. You can actually see there's a little LED. This is LED number 4 that's blinking. And when that LED is blinking, that's actually how I know that this particular device is transmitting. So this is good to go, and what I'm going to do is set it next to my antenna, and I'm going to do it pretty close so I can get a pretty good signal reading. So I'll just set it down there. And what we can do is pan over to the screen. This screen's connected to the same system. And I'm looking at a spectrum analysis view of 20 megahertz at 2.43 gigahertz. And so to give you a better view of this, we're actually going to move to a screenshot kind of program where you can look at a better view. So now that we're on the screen capture view, we can zoom in and look at the screen a little bit better. Now what I want to point out first of all is that we're centered at 2.43 gigahertz. And all I'm doing is using this demo panel to figure out which channel my transmitter is transmitting on. And so the way I would do this is I'll look at a wider view of the ZigBee entire bandwidth between 2.4 and 2.46 gigahertz. And if you look on your screen, you'll see periodic spikes from anything using these particular bands. Now, there's two things you'll notice here. One is that periodically you'll see spikes that are about 20 megahertz wide. Now, those spikes are actually from the Wi-Fi network, which uses about a 20 megahertz channel. However, also at 2.43 gigahertz, I'll see a much higher amplitude spike periodically as well, and this one is only about 4 to 5 megahertz wide. Now, the narrower spike is a ZigBee transmitter. So one of the things to do when using this type of a graph is make sure you can identify the ZigBee signal simply by analyzing the signal bandwidth. So now that I've confirmed that I'm on 2.43 gigahertz, I'll close this view, and then we'll go to our analysis software. So I'll click on Exit. Now the analysis software that I'm using is the YPAN signal analyzer, and this is from CSolve software, which is an alliance partner of National Instruments. So to acquire my signal, I'll first click on Mode, then Online NI, and I'll choose my down converter device, my digitizer device, my carrier frequency, coupling should be fine. My reference level is set to 0 dBm. That should be fine as well. I'm using a preamp to amplify the signal by quite a bit. So I'll click on Acquire, and in this case I'm doing a multiple acquisition record. And so I'll have to select the number of packets that I want to acquire, and I'll just choose 10. So click on Acquire, and then Done. So once I do that, the software will take me to this multi-view analysis tab. And all it's doing is it's doing a continuous analysis by scrolling through each of the 10 packets. For each of these, I can show a couple different plots, from a power spectrum to a constellation plot to an EVM plot, as well as see various measurements for each of these, for each packet. Some of the common measurements are error vector magnitude as a percentage, the IQ magnitude error, phase error, peak EVM, and peak EVM offset as well. And so what I'm going to do is click on the Measurements tab to zoom in a little bit closer on some of these specific measurements. So first I'll click on Power Spectrum Density. Now, power spectrum density is a measurement that's used to characterize the signal with respect to a spectrum mask. Now, the ZigBee standard specifies that the transmitter should not transmit anything higher than 30 dB from the highest peak within about a 6 megahertz bandwidth. So you can see I have the spectrum mask centered over the peak signal power, and then it goes down for about 30 dB. Now you can see clearly from this screen that of all the 10 packets, none of them are outside of the mask. And so this particular ZigBee transmitter is completely compliant in this regard. So next, I'll choose the constellation plot. The constellation plot shows me information about the demodulated data. And these red dots, right here, 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 and here, are each of the recovered symbol locations of a modulated signal. Now you'll notice here as well that because ZigBee uses offset QPSK, or offset quadrature phase shift keying, all of the transitions from one symbol to the next follow this circular motion around the outside rim. What that means is that the power or the amplitude of the transmitter never changes, but simply the phase changes instead. And so by not having any amplitude changes and essentially no transitions through the middle of the diagram, we can actually transmit information at lower power. So because a ZigBee transmitter is designed to be a low power device, offset QPSK is used for the modulation scheme. So that's kind of interesting to analyze. If I want, I can go to a single packet analysis, and we can stop the screen and look at one packet. So next, I'll go to EVM, and that stands for error vector magnitude. And what this particular plot shows me is the error vector magnitude of every recovered symbol. And so you can see of the 700 and looks like I have about 730 symbols. You can see my EVM is vary slightly from one symbol to the next. But this is also used that if you want, you can look at the peak EVM value and as well as the index of that value. Finally, I'll go to the Mac view, and what this does is it tells me actually the digital information that's inside the ZigBee packet. You can see that this particular packet is a beacon packet, or a beacon frame, and I can look at the actual body of that frame to see what type of information was actually being sent. And so you can see as in hex code the information that was sent from my transmitter. So these are 4 basic views of the signal, and what I'll do is I'll go back to the multiple graphs view and go back to continuous mode. So I hope this is helpful and gives you a little bit more information on the types of measurements that you make on a ZigBee transmitter, and also a little bit more information about why those measurements are made. For more information, please feel free to contact me or just talk to your local NI representative. Thanks, and have a great day.